Hi viewers, welcome to my class on mechanics of materials. In today's class, we will work out another numerical example to draw the shear force and bending moment diagram for a beam subjected to UDL. Draw shear force and bending moment diagram for the loading pattern on the beam shown in figure. Indicate where the inflection points are located. Also indicate the maximum bending moment with its magnitude. So this is a beam which is subjected to UDL of intensity 5 kN per meter throughout its length, and the beam is supported symmetrically 2 meters from either end. It is an overhanging beam, overhanging on both sides. Now to find out the reactions, you can consider the symmetry of these supports, and the loading is also symmetrical. So if you consider axis like this passing through the center, the loads on either side are symmetrical. Even the supports are placed at equal distances from this y-axis. So when it is symmetrical like that, the total load will be shared equally by both the supports. And we know that reaction here is vertical and the load is also vertically downward, so reaction to the hinge support is also going to be vertical. So these vertical reactions will be equal and it will be half of the total downward load. So total downward load can be calculated as intensity multiplied by the total span. So 5 kN per meter is acting over 14 meter length. So 5 into 14, or that is 70 kN is the resultant load which can be replaced at the center. So 70 kN is acting downward. Out of 70 kN, each support has to take 35 kN. So that way you can easily find out the support reactions. You can also go by the summation of the moments. So total load due to UDL is 5 into 14 or 70 kN. Due to symmetrical loading, the reactions at the supports A and B are equal, and you can find out RA or RB as half of the total downward load or 35 kN. Or if you go usual way, you can replace UDL. Total UDL is 14 into 5. So that will give 70 kN. 70 kN acting at the center of this overall distance. So because UDL is acting for the entire length 14 meter. So 14 divided by 2, that is 7 meter from this end or 7 meter from the right end. So 7 meter away from the point C, that is left end, you can place this resultant load. So that is 70 kN is acting at a distance of 7 meter, and this support reaction is vertical and reaction at A is also vertical. Now to go for moment summation, you can take moment summation with respect to A. One of the supports you should choose as a moment center. Don't choose C as a moment center. No advantage in choosing C as a moment center because RA and RB both will come into that equation. So to eliminate one of the unknown, you should either choose A or B as the moment center. So choosing A as a moment center, 70 into this distance you should calculate, totally 7, you should subtract 2, which will give 5 meter. So 70 into 5, which will be producing a clockwise moment, minus, this is anti-clockwise, so minus RB into 10 is equal to 0. That is a moment summation. So there are only two loads. This load is not producing any moment with respect to A. We have chosen this as a moment center. So 70 is producing a clockwise moment. 70 into 5 minus RB into 10 is equal to 0, or RB is equal to 35 kN. Now once you get RB 35 kN, out of total downward load, RB is taking half, that is 35, The remaining half has to be taken by support A, or Ra will be equal to 35 kilonewton. So whichever way you want, symmetry will get only once in a while, and it is symmetrical. Loading and placement of supports are symmetrical. You can find out the reaction easily by looking at the diagram. You can easily find out the reactions. Now let us calculate the shear force. But shear force you have to calculate for the UDL. You cannot draw the shear force diagram for this. Acting as a point load, that will produce a different shear force diagram and bending moment diagram. So you should not draw the bending moment diagram or shear force diagram by keeping it as a point load. For a distributed load, you should draw the shear force and bending moment diagram. Now let us calculate the shear force at various points. Now when UDL acts, you have to find out the shear force either end of the sections. So here CA is the first section. So here in CA you have to calculate immediately right of C and immediately left of A. And next portion is AB, where you have to calculate immediately right of A and immediately left of B. And again for BD, immediately right of B and immediately left of D. So 6 different sections you have to calculate the shear force. Now right of C, if you take, this part of UDL is infinitesimally small, so there is no load immediately left side of the section plane. So you are taking the section plane right of C, but looking for the forces on left side of that section plane. So there is no force there, and shear force will be 0 at right of C. So taking that section plane, looking for the forces here, there is no force. This part of UDL is infinitesimally small, so shear force is 0. Shear force right of C is 0. Now let us take a section here immediately left of A without considering this reaction. Immediately left of A. There this part of UDL will come. Okay, this part of UDL will come, and it is for 2 meter length. 5 is the intensity, 5 kilonewton per meter is intensity. It acts for 2 meter, so 5 into 2 or 10 kilonewton will be the load. So 10 kilonewton will be the shear force, but it is downward, so minus 10. So let us write down that shear force for this section. This part of UDL is minus 5 into 2, minus because it's downward, so minus 10 kilonewton. Now next you have to consider a section here. If you take a section here, already we got the shear force for this section as minus 10, and when you move to the immediately right of A, the additional load coming is this reaction 35. So you can get immediately right of A, the shear force as minus 10 here plus 35, which will give 25 kilonewton. So right of A, shear force right of A, that is this point, this part of a load, we already calculated that. So this part of load is producing downward shear force minus 10 plus 35, which will give 25 kilonewton. Next section is left of B. Left of B, additional load if you take, that is another 50 is coming, 50 downward load due to UDL. UDL is 5 kilonewton for 10 meter. So additional load coming is 50 kilonewton downward. So from this section to this section when you move, additionally there is a 50 kilonewton which is downward, so minus. So whatever shear force you add for the previous section minus 50, that will give the shear force left of B, that will give minus 25. Minus 25, that is shear force left of B. But here I have calculated a shear force instead of taking two separate parts. The total UDL I have taken, that is for 12 meter, minus 5 into 12 because it's downward, minus 5 into 12 plus 35, which will give minus 25. So this is the summation of all the loads left side of that section. Next we have to take a section immediately right of B. Immediately right of B, you can see that minus 25 is the shear force here. When you move to the right of B, additional load is plus 35. So minus 25 plus 35, or shear force immediately right of B is going to be 10 kilonewton. Here I have summed up all that forces. So minus this UDL is minus 5 into 12 meter. Okay. So that is minus 5 into 12 plus 35 plus 35. So which will give 10 kilonewton. When you move from this section to immediately left of D, it's 2 meter. 5 kilonewton per meter is intensity. It acts for 2 meter. So 10 kilonewton, and it's downward. So minus 10. So whatever value you have here, that is 10. Shear force right of B is 10. 10 minus 10 will give the shear force here 0. Immediately left of B, it will be 0. And when you move to D also, it will be 0 only. Unless you have a point load here, there will not be any change in shear force at D. So these are the shear force calculation for various sections. So left of D, you get minus 5 into 14, total load 5 into 14 plus 35 plus 35, so which will give 0. Next you have to calculate the bending moment. Bending moment you have to calculate at C, A, B and D, but C and D we know bending moment is 0. At C, bending moment is 0 because it's extreme and no couple is acting. At C, bending moment is 0. Now to calculate bending moment at A, you have to look for the loads left side of A. Left side of A, only UDL is there. And UDL, and the total UDL is, intensity is 5. It acts for 2 meter. So 5 into 2, 10 kilonewton. And 10 kilonewton will act at the center of this 2 meter. Okay. So I am only considering this part of UDL. So 5 into 2, 10 kilonewton acting at the center of 2 meter. That means 1 meter away. So 10 kilonewton acting at a distance of 1 meter. Now that is a downward force. This 10 kilonewton is a downward force. It will produce a negative moment with respect to point A. So minus 10 into 1, that will be the moment at A, bending moment at A. Minus 10, that is 5 into 2 into the distance 1. So minus 10 kilonewton meter, that is the bending moment at A. Next you have to calculate the bending moment at B. Bending moment at B, when you take this section B, you have two loads. One is UDL, another one is this reaction at A. So UDL you can take it as a single load. Okay. Don't consider this a separated 2 meter length, one load that is 10 kilonewton, another 10 meter, another load 50 kilonewton acting at the center of this. You can treat it as a single load. For 12 meter, it is 60 kilonewton. Okay, 12 into 5, 60 kilonewton. This part of UDL, 5 into 12 meter, so 60. For 12 meter, it will act at the center of 12 meter. That is 6 meter from here or 6 meter from here. We need the distance from B, 6 meter. So 5 into 12 meter, that is 5 into 12 into 6. Okay, 5 into 12 into 6, and that will produce a negative bending moment. So minus 5 into 12 into 6. 5 into 12 give the load and 6 meter away from the moment center. So that will give the bending moment due to UDL. Now 35 will produce a clockwise moment. 35 into 10. That will give the bending moment at B as minus 10 kilonewton meter. Now bending moment at D is 0. So this will give the bending moment at various points. Now apart from this, wherever shear force goes to 0, there you should calculate the bending moment. Since wherever shear force is 0, bending moment will have a peak, and that point is important in the diagram. So after drawing the shear force diagram, if a shear force is coming to 0 under this UDL somewhere, then you have to calculate the bending moment corresponding to that point. Now let us draw the shear force and bending moment diagram now. Now we have calculated the variation of shear force in the section CA. We got the shear force right of C as 0 and left of A as minus 10. So 0 to minus 10 is the variation for CA, and due to UDL, shear force will vary linearly, that is straight line variation from 0 to minus 10. So 0 to minus 10 you show. And for the section AB, from right of A we got plus 25 and left of B we got minus 25. So for the variation of AB is plus 25 to minus 25. So you can show plus 25 to minus 25. So here left of A is minus 10, right of A is plus 25. So minus 10 to plus 25 at A it has to change. So minus 10 to plus 25 you can show the straight line, vertical line. And this change is happening because of this vertical force. So vertical reaction here, any point load at any point will change the shear force suddenly. So this is a sudden change from minus 10 to plus 25. So total change is 10 plus 25. 35 is the total change. So that is 25 minus minus 10. So 35. 35 is the change. So 35 is the upward force. So upward force will produce an increase in shear force by that amount. Okay. So at this point the shear force is increasing from minus 10 to 25. And this section it is changing from 25 to minus 25, and it is linear variation, so you can show linear variation. And the section BD, from B to D, it is right of B it is plus 10, left of D is 0. So 10 to 0 and again linear variation, 10 to 0. But here at left of B we have minus 25, right of B plus 10. So minus 25 to plus 10. So that changes at B. So you can join it by a straight vertical line. So that again the change you can observe because of this point load 35 kilonewton. The change is 35. Increase because it's upward load, increase by 35. So that is 10 minus minus 25. The total change is 35. So wherever point loads comes, there will be a sudden change in shear force, and if it's an upward load, shear force will increase. If it's a downward force, shear force will decrease at that point. So this completes the shear force diagram. We have calculated the bending moment at 4 salient points C, A, B and D. C and D we know bending moment is 0. At A you got minus 10 and at B got minus 10. So 0 to minus 10, and when shear force varies linearly, bending moment variation is parabolic. Wherever UDL, under UDL, shear force variation will be linear and bending moment variation will be parabolic. So 0 to minus 10, that is a variation, and you have to show a parabolic variation. And here at B minus 10 and D 0, and again minus 10 to 0, you should show parabolic variation. Parabolic variation you should always plot it like this. Parabolic variation for a bending moment curve, you should always plot it like this with the concave side down. Okay, you should not draw in the other way. Here similarly you should not draw it like this. And here in this portion again UDL is acting and shear force is varying linearly, so bending moment variation is going to be parabolic. But while plotting this parabolic variation, you don't know how this goes. So minus 10 to minus 10, you cannot draw a straight line. This variation is a parabolic variation, so you can plot it like this. Okay, minus 10 to minus 10, you can plot it like this, or you can plot it this way. But plotting this, always you will have a peak. So this peak point is coming where shear force is 0. We have already learned that when shear force is 0 at any point, bending moment curve will have a peak, or bending moment curve will have a slope 0. So shear force is 0, here bending moment curve is having a slope 0, and this point is going to be a peak, and this peak point, the value of bending moment has to be marked. Without that, bending moment diagram will not be complete. So this peak may have a maximum value of bending moment, and in this case it is coming maximum. It can be minimum if curve goes like this, and you may have a peak, a very small negative value. So that is also possible, but peak may happen to be highest bending moment or maximum bending moment. So always wherever shear force crosses the x-axis, there you should calculate the bending moment. Here also shear force is changing its sign, but already that point is a salient point, and you have already calculated the bending moment there. And here again it's changing, here you have already bending moment there. But under UDL, especially when it changes, you will have slope 0. Here slope is not 0, it is a sudden change, discontinuity for the load. Okay. Now, wherever under UDL or under UVL shear force changes its sign, other than the salient points, mark points, you have to calculate the bending moment and mark it in the diagram. So, to calculate this value, you should know at what point this shear force is coming to 0, at what distance from left end the shear force is coming to 0. In this case, by symmetry, by observing this is 25, this is 25, and by observing that, you can see that this is coming at the center of 10 meter. So that means this is 5 and this is another 5, or totally it will be 7 meter from the left end. So at the center of the beam, shear force is coming to 0 at the center of the beam. That is can be observed from the symmetry. The loading itself is symmetrical, placement of supports is also symmetrical, and shear force diagram also you can observe, and you can immediately conclude that the shear force will come to 0 at the center. That way you can identify and locate this point, or you can write down the shear force equation for this section. Because this point is coming in the section AB, you take a section in the portion AB at a distance x. X can be a variable, x changing from 2 meter, at A it's 2 meter to 12 meter. So x value can be from 2 to 12. So shear force for this section is two loads are there left side. One is downward UDL and another one is upward this reaction. You will get the shear forces. So 5 kilonewton for every meter. So for x meter it is 5x. So downward load is 5x, and that is a negative shear force. So minus 5x, and this will produce a positive shear force plus 35. So that is the shear force equation. Shear force equation is minus 5x plus 35. So after writing that shear force equation, you can substitute values of x 2 to 12. 2 if you substitute, you will get the shear force here. 12 if you substitute, you will get the shear force at the right end. We have written this not to calculate the shear force. We already know the shear force at this point. So once you know the shear force, you can find out the distance, at what distance it's coming to 0. Okay. So this can be used in two ways. If you know x, you can find out the shear force, or if you know the shear force, you can find out x. But at this point you know shear force is 0, substitute shear force is 0, you will get the value of x. So x is 7 meter by substituting x is 7 meter. That is our observation at the center of the beam, 7 meter from left side. Now after identifying that point, you can find out the bending moment corresponding to that point. Bending moment you can calculate by writing the bending moment equation and substituting. Bending moment for this point you should find out, and this point is in the section AB. You can write a general equation and substitute x as 7, or you can directly calculate the bending moment at a distance of 7 meter. Okay. So I'll write the general equation. Many a time you have to write the general equation. And the bending moment is coming to maximum in the same section AB. So I have already taken a section. Now you can write down the bending moment equation. So we have already done the shear force summation, and shear force summation is a force summation. So these are the forces. Now you have to find out the moment for that forces. Only you have to multiply these values with the distances where it acts. So the load is 5x. Okay, that is will produce a negative shear force. It's already there, minus 5x. You need to multiply with the location of that load. So it is x meter. The resultant load will at a distance x by 2, center of x. So minus 5x into x by 2, that will be the moment produced by that force. Okay, minus 5x into x by 2, that will produce an anti-clockwise moment. Minus 5x into x by 2, that will be the bending moment of that force with respect to this section. Now 35 will produce a clockwise moment, plus 35 is already there. Now only distance you should multiply. The distance is, overall is x, you should subtract 2. So that will give this distance x minus 2. So 35 into x minus 2. So minus 5x into x by 2 plus 35 into x minus 2. That will give the bending moment for that section. Minus 5x into x by 2 plus 35 into x minus 2. Now you can reduce this into minus 2.5x square plus 35x minus 70. So this will give the bending moment equation for the section AB, and you can use it for any point between A and B. At any point you can calculate the bending moment using this equation. We need this particular point, that is 7 meter from left end. You already got that location, and you have to substitute x as 7. Now substituting x as 7 meter, you will get the value of bending moment as 52.5 kilonewton, and you mark it in the diagram. Okay, so that will complete the bending moment diagram. Now once you plot the bending moment diagram, you will observe that the bending moment is crossing that x-axis at 2 points, or bending moment is changing its sign at 2 points, changing from minus to plus here and plus to minus here. These points where bending moment changes its sign on a beam is known as point of contraflexure or point of inflection. The points where bending moment changes its sign is known as point of contraflexure or point of inflection. So it is not the point where bending moment is 0. Bending moment is 0 here. This is not a point of contraflexure. So bending moment changes its sign. Okay. And these 2 points are known as point of contraflexure. And if it is asked to find out the point of contraflexure, you need to locate these distances. This peak value of bending moment you should always calculate and write it in a bending moment diagram. You should always calculate and write it in a bending moment diagram. Without that, bending moment diagram will not be complete. But this location of point of contraflexure, if it is asked, you should calculate. Okay. So you need to find out the distance from the left end or from the right end. Okay. So we will always write the equation from left end. So we can find out the distance from left end, this distance, and again this distance to this point from left end. What is the distance? So that is point of contraflexure. So you can locate the point of contraflexure. So first thing is you have to identify which section these points are coming. This point of contraflexure is coming in the section AB. It is coming in the section AB itself. Both the points are in the section AB. So this is a bending moment curve, and bending moment is coming to 0 here. These 2 points, bending moment is coming to 0. So you have already written the bending moment equation. And bending moment equation can be used to calculate bending moment if you substitute x, or bending moment if you know, you can solve for x. So here we know the bending moment. Bending moment is 0 at these points. Okay. You can calculate the points of counterflexor. You can calculate these points, that is points of counterflexor, by substituting bending moment as 0. So let us do that. So we have to write down the bending moment equation for the section AB. We have written that bending moment equation. Okay, it's already shown in the previous slide. We have already written to calculate the maximum bending moment in that section. The same equation can be used to locate the point of counterflexor. Okay. Now this equation is the bending moment equation. Bending moment equation is minus 2.5 x square plus 35x minus 70. So that you can equate to 0 to locate these points. You can multiply then by minus 2, that will make it this plus 5x square. Minus 2 you have multiplied, minus 70, minus 2 and you multiply, plus 140 is equal to 0. Then you can solve for x using the equations. Solution for the quadratic equation is minus b plus or minus root of b square minus 4ac whole divided by 2a. So substituting b is minus 70. So minus b means plus 70 plus or minus b square minus 70 square minus 4 into a into c, okay, divided by 2 into a. So that will give two values, because since it's a quadratic equation, it will give two values, 2.417 and 11.583. So you are getting the distance 2.417, that is the first point, 2.417, and 11.583. And from the symmetry you can observe the remaining distance from the right hand is again 2.417. So these points are symmetrical. So you got the points of counterflexor. So these points you have located and you can mark in this diagram. So this is a shear force and bending moment diagram for the beam, and we have located the point of counterflexor. We have marked the maximum bending moment. So now the diagram is complete. That's all for today. Thank you for watching.